Environmental contamination has risen in recent decades as a result of increased anthropogenic activity. Bioremediation is the process of using microorganisms to remove or degrade pollutants from the environment. Bioremediation is highly involved in degradation, eradication, immobilization, or detoxification diverse chemical wastes and physical hazardous materials from the surrounding through the all-inclusive and action of microorganisms. The main principle is degrading and converting pollutants to less toxic forms. Bioremediation can be carried out ex situ and in situ, depending on several factors, which include but not limited to cost, site characteristics, type, and concentration of pollutants. Hence, appropriate bioremediation technique is selected. Bioremediation is the most effective, economical, eco-friendly management tool to manage the polluted environment. All bioremediation techniques have its own advantage and disadvantage because it has its own specific applications. There are various treatment methods or approaches available within the context of bioremediation processes. The basic methods of bioremediation include biostimulation, bioaugmentation, bioventing, biopiles, and bioattenuation. Bioremediation of landfill leachate with isolated bacterial strains. Household, industrial non-hazardous, and commercial solid waste, as well as non-hazardous sludge, are all regularly disposed of at urban solid waste landfills. Despite its potentially dangerous effects on the environment, sanitary landfilling is still used in waste management plans. Sanitary landfilling often has cheaper operating costs than alternative techniques, such as incineration. After being dumped, waste may go through a number of biological and physicochemical transformations, creating leachate, a very contaminated effluent. This type of effluent has the potential to harm nearby ground and surface water, as well as soil. Landfill leachate has a high chemical and biological oxygen demand and frequently contains large amounts of organic pollutants, heavy metals, toxic chemicals, ammonia, and inorganic materials, as well as refractory compounds such as humic substances and developing contaminants. Leachate from landfills can have different features depending on how they degrade, the temperature, the hydrology, and how old they are. Environmental contamination and health problems are frequently associated with improper management of landfill leachate. In open dumping and sanitary landfills, reducing dangers to the environment and human health is a serious concern. Biological strategies, as well as chemical and physical processes, are appropriate key techniques for landfill leachate treatment. The bacteria used in the bioremediation of landfill leachate were chosen based on their resistance towards sodium chloride, heavy metals, and how they treat ammonia, phosphate, and nitrate. Firstly, the bacteria used are halotolerant, where they are capable to survive in high silt concentrations because the landfill leachate has high concentrations of NaCl. These halophiles have the ability to keep the balance of sodium into the cytoplasm and counteract the osmotic pressure of the external environment given by the osmotic pressure of the salty environment. Besides, the bacteria chosen are resistant to utilize heavy metals such as copper, zinc, and manganese that can pollute the groundwater and surface water. The decomposition of landfills releases toxic gases such as ammoniacal nitrogen into the environment, especially into nearby groundwater systems, will lead to negative impact on the environment. As a result, the bacteria selected in the bioremediation of landfill leachate are capable of growing various concentrations of ammonium, nitrate, and phosphate. It is highly challenging to extract ammoniacal nitrogen using conventional physical or chemical techniques because of its considerable chemical stability. Therefore, the primary technologies employed to remove ammoniacal nitrogen today are activated sludge techniques. Regardless of the method employed, adapted nitrification or nitrifying bacteria can successfully remove the majority of the ammoniacal nitrogen present in leachate. Nitrification is the process of converting ammonia into less toxic nitrites and nitrates by the nitrifier's bacteria. This process should be carried out in the aerated and controlled temperature and pH facilities for the most effective result. However, nitrites and nitrates are still undesirable in the environment, So the next step is conducted in order to convert nitrates into nitrogen, which will be released into the atmosphere through the process called denitrification. Both of this essential process can be conducted in a membrane bioreactor, MBR, that allow the landfill's leachate to be treated before being released into the streams. Lactobacillus species are the example of bacteria that are both phosphate solubilizers and ammonia oxidizers, while bacillus are the species that has the potential in the bioremediation in soil. NITROSOMONAS is a microbial organism that does nitrification. In this biological process, reduced nitrogen molecules are successively oxidized to nitrite and nitrate. The primary agents in the nitrification process are two kinds of autotrophic nitrifying bacteria. Fundamentally, bacteria from the wastes and other nitrifying bacteria convert ammonia from landfill's leachate to nitrate. Ammonia is converted to nitrite during the first step of nitrification when ammonia oxidizing bacteria are present producing nitrogen dioxide. In the second stage of nitrification, the bacteria oxidized nitrogen dioxide to nitrate. Then the process is followed by the conversion of nitrate to nitrite and nitrite to nitrogen gas by microorganisms is known as biological denitrification. When there is enough organic matter and neither dissolved oxygen nor molecular oxygen is present, heterotrophic bacteria often carry out this conversion. The oxygen in the nitrate serves as a source of oxygen for the bacteria. Nitric oxide, nitrous oxide, or nitrogen gas are the three different types of nitrogen gas that are created. The subsequent aeration process removes the nitrogen gas produced during denitrification from the wastewater, resulting in the net removal of nitrogen.